welcome to the Unit 7 summary review video for AP Statistics. I'm Michael Porinchak, and I'm ready to talk to you about everything you need to know that comes out of this unit. Now, Unit 7 is over inference for quantitative data focusing on means, because when you have quantitative data, that's data in numerical form, the most common thing we do with those is, well, find the mean. Okay, so we're going to be focusing on means in this video for sure, specifically sample means, and how we could use sample means to give us some estimates of what the population mean can be. That's what the unit's all about. Now, before we begin, let me give you two big things I want to tell you. First, this is just a review video. I don't go into every single teeny tiny detail for Unit 7. I just try to focus on the big things that you need to know in preparation for your unit exam in class and for the AP Stats exam in May. Second, I've created an awesome study guide for you that goes over everything in this unit with tons and tons of practice problems. So if you're interested in that study guide, check out the Ultimate Review Packet at ultimatereviewpacket.com for AP Statistics. And you could download, print, however you want to access the study guide and follow along with me, pausing or just doing the problems all at the end. But the study guide is going to really give you that great practice that you need to be confident in your abilities when it comes to taking a unit test or the AP exam in May. All right, let's get ready to dive right into Unit 7. First up is topic 7.1. This is a very short intro topic. Basically just reminds us that samples do one thing really well. They vary. Just because you get a sample mean of 7.1 doesn't mean that the population mean is 7.1. We actually have a name for this. It's called sampling variability. That's just the natural variation that exists between the mean of a sample and the population mean. But sometimes people just call this error. Not error like you did anything wrong. It's just completely natural error. It's just sampling error. A sample mean is not going to match the population mean perfectly. Now, this unit covers two huge concepts. First, confidence intervals for a population mean, and second, significance tests for a population mean. Now, both of these concepts hinge on sampling distributions. Now, to build a sampling distribution, you need to know the true population mean and the true population standard deviation. But what if we don't know those things? Well, that doesn't mean the sampling distribution doesn't exist. It still exists. We just have to kind of estimate and think about what it could look like, because that sampling distribution is important for us to understand that there are many possible sample means out there, and ours is just one of them, and we really hope it's close to the population mean. Therefore, we're pretty accurate that our sample mean is going to help us make some estimates about what that population mean could look like. Now, since everything in Unit 7 hinges on the idea of a sampling distribution, which we usually approximate with a normal distribution, however, in this unit, we're going to be using the t-distribution. Now, the biggest reason for this is that when we are using a sample standard deviation S as an approximation for the standard deviation of the population sigma, the t-distribution is just, well, better. It's a little bit more accurate. Now, the t-distribution is very similar to the normal distribution. The area out on the bottom and left tails is just a little bit bigger. Now, as your sample size increases, your degrees of freedom increase. Now, the degrees of freedom directly relate to the different t-distributions that are out there. Although there's only one normal model, there's different t-distributions for every degree of freedom. And your degrees of freedom is simply your sample size minus 1. And as your sample size goes up, the ends of that t-distribution get smaller and smaller, and it looks more and more like the normal distribution. But that's the basic reason why we have to use a t-distribution in this unit when we're working with means. One more time, it's because we have to use the sample standard deviation S as an approximation for the standard deviation of the population sigma. And think of it as just a twin brother of the normal distribution, but just a little bit more approximate, and a little bit more accurate, I guess we could say, when we are using the sample standard deviation S. So topics 7.2 and 7.3 are all focused on constructing a confidence interval to find a population mean. First, let's talk about how to actually construct this confidence interval. It's a 4-step process. Let's talk about step 1. Step 1 is naming the test. It's a one sample t-interval for a population mean, but then you want to give some context as to what that population mean you're trying to find is. Step 2 is checking the conditions to ensure that our sample distribution can be constructed. Condition number 1, of course, sample's got to be random to avoid bias. Condition number 2, the size of our sample needs to be less than 10% of the population so we can assume independence. And condition 3 is that our sample needs to be big enough. Now, we are going to be using that t-distribution that I mentioned, but we still need to be big enough. And there's 3 different ways that a sample could be big enough. First, if the population that the sample was taken from is known to be normal, then any sample size is big enough, even a sample size as small as 1. Or if our sample size is 30 or larger and it was taken from a population that was unknown or specifically not normal, then the central limit theorem says we're still good to proceed with a sampling distribution. Now, the other scenario is when our sample size is below 30 and the population is not known or specifically non-normal. This does sound like it would be a death sentence. Well, it's not. As long as we check our data and make sure that there's no major outliers and no major skews. You can check this with a simple histogram, a dot plot, or a box plot. And if you see no major outliers, no major skews, you're still allowed to proceed with a sample that's quote-unquote big enough. Now, the third step to construct a confidence interval for a population mean is to actually construct it, doing the math with this very simple formula. X bar, that's our sample mean, that's going to be the start, that's going to be the actual middle of our confidence interval, and from that X bar we're going to add and we're going to subtract our margin of error. The margin of error is the product of 2 things, the critical value, that's our T star, and the standard error, which is S, the standard deviation of our sample, divided by the square root of our sample size. Now, in a problem, you're either going to be given the mean and the standard deviation of your sample, as long as the sample size, or you're going to have to actually calculate it, which means that you're going to be given the data, and you can import that data into your calculator to get the mean and the standard deviation. Now, the only other value that you are going to have to find is your critical value T star. Now, you could use what's known as a T table to look that up, or you could use invert T on the TI-84 calculator. Now, when you go to invert T, it's going to ask you for 2 things. First, it's going to want the area at the bottom, or the area to the left. So for example, if we're 95% confident, that means 5% of samples are left out, 2.5% at the bottom, and 2.5% at the top. So the area to the left would be that bottom 2.5%, so we import 0.025. And then it's also going to ask for degrees of freedom, because remember, every sample size has -1 degrees of freedom, and based on the degrees of freedom, you're going to use a specific T distribution. So make sure you enter your degrees of freedom in as well, which is, again, just sample size -1. That's how you're going to get your T star. Now, the fourth and final step to constructing a confidence interval for a population mean is interpreting what your interval means in context. So we want to make sure we first start off with stating our level of confidence. So you say something like 95% confident that the true population mean of fill in the blank with the context in terms of what you're trying to find. And then that's what the interval is. It's going to be somewhere between the bottom and the top of that interval. Now, before we dive into an example of exactly what we just went over, let's quickly talk about a couple more details. First, sample size matters. Bigger samples vary less, so bigger samples should be closer to the truth. Meaning that when you have a bigger sample, your margin of error is going to shrink and your confidence interval will become more narrow. So always use bigger samples. They will produce more accurate, smaller confidence intervals. Now, the other thing we could do is adjust our level of confidence. Typically we use 95. We could also use 96, 98, or 99. Now, the more confident you are, the wider your interval is going to be, because to try to capture more samples, you're going to need to get wider. Now, the best thing you could do is use a high level of confidence, which on the surface sounds like it's going to make a wider interval. But remember, if you increase your sample size, you're going to be decreasing the size of that interval, becoming more and more accurate. So we love high confidence, but we also love bigger samples because they are more accurate. All right, now let's take a look at a full example of exactly how to construct a confidence interval for a population mean. What is the mean amount of time a name brand AAA battery lasts? To find out, Becky selects a random sample of 55 name brand AAA batteries and runs them each in a flashlight until the flashlight no longer operates. She records the time of the 55 batteries lasted and then calculates the mean and standard deviation of her sample. The mean of her sample was 348.6 minutes and a standard deviation of 23.8 minutes. Construct a 99% confidence interval for the population mean amount of time that the name brand battery lasts. Now the first step is going to actually be, again, naming it in context. This is a one sample t interval for the mean amount of time in minutes that all brand name AAA batteries will last in the particular mentioned flashlight. Try to be as specific as you can when you're doing step one, using that one sample t interval name, but then giving context to what you're trying to find. Step two, the sample of 55 batteries was randomly selected to avoid bias. Condition number two, the sample of 55 name brand batteries is assumed to be less than 10% of all name brand batteries, so that we can assume independence. And the third condition is, well, we don't know whether the population is normal or not, it never said, but our sample size is bigger than 30, it's 55, which is bigger than 30, so we are safe to assume that we could use a t-distribution to explain the sampling distribution with 54 degrees of freedom. Next comes actually building the interval, which again, I think is the easy part. We're going to start off with our formula, and on the AP exam, they do love when you show that formula first, x bar plus or minus your t star times s divided by the square root of n. Now we're going to fill in the mean from our sample, that's our point estimate of 348.7. The standard deviation of our sample is 23.8, and the sample size was 55. The only thing we have to do is go and look up our t star for 54 degrees of freedom and 99% confidence. You could use a t chart, or you could go to invert t on your TID4 calculator. Now, 99% confident puts 1% on the outside, 0.5% at the bottom, 0.5% at the top. So if we go to that invert t, the area at the bottom is 0.005. That represents that 0.5%. And then we're going to type in 54 degrees of freedom, and that's how I got the t star of 2.6700. Now, multiply the t star times your standard error to get the margin of error of 8.569. Add and subtract that to the sample mean, and we get a confidence interval of 340.13 to 357.27. Now it's time for that fourth step, interpreting our interval. I'm 99% confident that the population mean time that a name brand AAA battery will last in this flashlight mention is somewhere between 340.13 minutes and 357.27 minutes. That's it. That's how simple the four-step process can be. Now, I do briefly want to go over one more example with you, just because some different things can happen when you're working with means. So in this example, doctors try to figure out what is the mean systolic blood pressure for teenage athletes at rest. So he gets a sample of 22 teenage athletes, and he gets their systolic blood pressure while they're at rest. Now, in this particular problem, it's set up where I'm giving you the data. I'm giving you the actual blood pressures of these 22 male athletes. Now, in this particular case, why I wanted to show you this is because you are going to have to enter this data into your calculator to get the sample mean, x bar, and the standard deviation, s. Sometimes those numbers are straight given to you. Other times, the AP exam likes it for you to go ahead and figure that out on your own. Now, the other problem we have in here is checking our conditions. Because our sample size is 22, which is not bigger than 30, and we don't know that the population is normal. In this case, we are going to have to go ahead and look at a quick graph of our data to ensure that there's no skewness or no major outliers before we can move on. So again, here's a quick look at step one, which is nice and simple. Make sure you use context. Step three, got to be random sample, got to be under 10% of our population to assume independence. And notice we made a quick graph here just to show that, hey, no major skewness, no major outliers, so we're still safe to proceed even though our sample size is under 30. Then we're going to go ahead and build the interval using all of the data that we found. That's the sample mean and the standard deviation. And then finally, we're going to go interpret it. I'm 95% confident that the population mean systolic blood pressure for all teenage male athletes is somewhere between 111.47 and 117.80 mmHgs.
They told me that I would need to pay for mom's medicine and that prescription.
Now, two more big ideas that come out of these topics over confidence interval for a population mean. First, you need to be able to explain what exactly a particular level of confidence means. So for example, if they say, what does 95% confident even mean in regards to a problem? Well, it's not a probability. A lot of kids will try to say, oh, 95% is the probability that this population mean is in my interval. No, absolutely not. The idea is that the population mean is either in your interval or it's not. There's no probability attached to it. We're 95% confident that it's in there. Now, what does that 95% confident mean? Well, it's all about samples. Remember, that sampling distribution is showing you all possible samples. And we know that, for example, 95% of them are so close to the true mean in the center that when we get our sample mean and wrap an interval around it, we should capture the population mean, again, in 95% of samples. So basically it has nothing to do with probability, it has nothing to do with time, it's all about samples. If we look at many samples, every sample will produce its own sample mean, and that sample mean will create its own confidence interval. So basically we're going to have a lot of confidence intervals because every mean has its own confidence interval. And 95% of all of those confidence intervals will contain the true population mean, and 5% unfortunately will not. But those 5% are because of the samples on the far left or on the far right that are extremely unlikely, and those type of samples, well, shouldn't happen anyway, so we should be getting a sample mean somewhere in the middle, 95%, so we wrap a confidence interval around it, or 95% confident that the true population mean is in our interval. Now, this last big idea is this. Sometimes we like to work a little bit backwards. What I mean by that is we start a problem not by knowing the data, but by knowing the margin of error we want to achieve. Oftentimes researchers want a very small margin of error because a small margin of error means you're more accurate. Now how can you achieve a small margin of error? Bigger sample size. So what sample size do we need to achieve a certain margin of error is a very common question. Now how do we do this? Well, let's look at an example so I can explain. Marcus wants to estimate the population mean circumference of spherical marbles that his company produces with a 95% confidence interval and a margin of error of only 0.4 centimeters. What sample size would you need to achieve this margin of error? Now, past samples have shown a standard deviation of 1.7 centimeters. All right, so first, we're given the margin of error, and we're trying to determine what sample size. So we're going to use the formula for the margin of error, which is just the back part of our confidence interval idea. It's just the product of t star times the standard error, s divided by the square root of a. That's our margin of error. So now we're going to use this formula for margin of error and just substitute in everything we know. We know the margin of error we want to achieve is 0.4 centimeters, so put a 0.4 on the left. The sample size is going to stay n, which is exactly what we're solving for. Now, we don't know S, the standard deviation of our sample, because we haven't looked at our sample yet. Marcus is trying to figure out how big the sample needs to be in the first place. But we do have this past information that says past data has shown a standard deviation of 1.7, so we could gladly put that 1.7 there. Now, what about t-star? Well, technically, we can't find t-star either. We do know 95 is the level of confidence we want, which puts 2.5% at the bottom. But we don't know our degrees of freedom because degrees of freedom comes from sample size, and we don't know our sample size. So in this scenario, we are going to have to go ahead and just use z-star. Now, for big samples, the difference between t-star and z-star should be pretty small, so we should be safe here, at least to give us a starting point as to what that sample size would be to produce that given margin of error. So the 95% confident z-star is going to be 1.96, so we can look that up in a z-table or use invert norm. Now all we got to do is solve this. So we're going to take the 0.4, divide by the 1.96, then we're going to multiply the square root of n over to the left-hand side, and then we're going to divide by the margin of error divided by the 1.96. So now we have s, that's 1.7, divided by the fraction of 0.4 divided by 1.96. All right, now the last thing we're going to do is get rid of that square root, and of course we're going to square both sides to do that. So if we square everything, we'll get our final answer. In rounding up, we get approximately 70 marbles. And if we look at 70 marbles, we should have a margin of error of roughly 0.4 centimeters. Next up is topic 7.4 and 7.5, which are all about significance tests for a population mean. Now, a confidence interval is used because we have no idea what the population mean is, and we're trying to use the interval to figure out what it might be. Now, in a significance test, we might know or have an idea what the population mean is, but we want to make a claim that it's something different. Maybe it's something greater, maybe it's something less, or maybe it's just something flat out different. And what we're going to do is get a sample to either find evidence to support that our claim is true, or a lack of evidence, and therefore we don't know that our claim is true. Now, the process is fairly simple, and it's 4 steps. Let's walk through each of those 4 steps right now. The first step of a significance test is the hypotheses. Here we have the null and the alternative hypotheses. But we also want to make sure in this step we name what we're doing. This is a one sample t-test for a population mean. And of course, we want to fill in some context, population mean of what? Now, we also want to define what that population mean is. Maybe it's the average amount of caffeine in a pill, or maybe it's the average amount of caffeine in a cup of coffee, who knows? Now, the null hypothesis is what we say status quo. Everything is the way it should be. The mean that we believe to be true still is in fact true. So we always want to use a mu equals whatever it said it was equal to in the problem. The alternative hypothesis is what we are claiming or what we are wondering. Now, there's three options here. We either wonder that the true mean is greater than what it was supposed to be, less than it was supposed to be, or simply not equal to what it was supposed to be. But in the problem, you will read what the population mean is supposed to be, and that number is always used in both the null and the alternative. We never use X bar, and we never use sample means within our hypotheses. The hypotheses are all about the population mean. The null is that it's the same as we think it is, and then the alternative is that, whoa, 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 we claim it's more, less, or not equal to. Now, if the alternative hypothesis is less than or greater than, we call these one-sided tests. One-sided lower if it's less than, one-sided upper if it's greater than. If we just flat out don't care if it's less than or greater than, just that the true population mean is something different, then we call that a two-tailed test, because it could be on the upper tail or the bottom tail, and we don't really care as long as it's something different. Now, the only difference in what you do is double your p-value if you have a two-tailed test, because your alternative is not equal to it. So at the very, very end, when you get your p-value, all you gotta do is make sure that you times it by 2 when you're working with a two-sided test. Now, step 2 of the significance test is to build the sampling distribution on the assumption that the given population mean is in fact true. And we also have to check the conditions for every part of that sampling distribution. So first, we're going to say, all right, the mean of all those sample means should be the true population mean that we said it was from the null hypothesis. But that's only going to be true if we have that condition met that our samples are random to avoid bias. The second thing we need is the standard deviation, but typically we only know S, the standard deviation of our sample, not sigma, the standard deviation of our population, which is why we're going to use standard error, which is actually going to make this a t-distribution instead of a normal distribution. Remember, those t-distributions are just a little bit more approximate and a little bit more accurate when we only know S, the standard deviation of our sample. Now, to utilize this formula, we do have to have independence, so we do have to check that our sample size is less than 10% of the population, so we can assume independence. Lastly, we need that shape to be that approximate t-distribution, and for that, again, we got to check one of 3 different parts. First, we need to be big enough. And we can be big enough because the population that we're drawing from is already known to be normal. In that case, any sample size is big enough. Or if our sample size is 30 or over, the central limit theorem says that our sampling distribution is already big enough, so we're good to go. The other scenario that we've already talked about in this video is if your population is unknown and your sample size is under 30, then what we need to do is really check our data very quickly and make sure there's no major skewness and no major outliers, and then we can still proceed. So building that sampling distribution and finding the center, the spread, and the shape is really important in step 2 of a significance test. All right, the third step of a significance test is to get that p-value. But how do we get that p-value? Well, we got to do a couple things. First, we need our X bar. We need the mean of our sample. That's either going to be given to us in the problem, or we're going to have to calculate it based on some data given to us. Now, what we really need to do is locate where that sample mean falls in our sampling distribution that we built back in step 2. Now, to do that, we're going to need a t-score. Why not a z-score? Well, remember, we're using a t-distribution to represent that sampling distribution, so we're going to use a t-score. But the good news is, the formula for a t-score, no different than a z-score. So we're going to take our sample mean x bar, we're going to subtract the assumed to be true population mean from our null hypothesis, and we're going to divide by our standard error, which is S. Once we have our t-score, we can figure out our p-value, which is the probability that any other sample mean is more extreme than the one we found, given that the null hypothesis is true. Now, to find that p-value, we're going to use t-CDF, not normal CDF, because we're, again, using the t-distribution. So when we go to t-CDF, we're going to choose an upper or a lower value. Now, be careful here. Make sure that if you have a positive t-score, we're going to have the lower value be that positive t-score. Then we're going to go an upper value of 99, acting like infinity, looking way above it. But if we have a negative t-score, we're going to have that be our upper value, and the lower value is going to be negative 99, looking way below. Because when we say the p-value is the probability of our sample mean occurring or more extreme, that means if we're positive, we're even more positive, even higher, even bigger. If we're negative, we're even lower, even more negative. All right, then the other thing you do need to add in there is the degrees of freedom, because remember, there's a different t-distribution for every different sample size, and they're based on the degrees of freedom, simple sample size minus 1. That's going to give you your p-value. And one more time, I really want to make sure you know what a p-value is the probability of any other sample mean being more extreme than the one we observed, given that the null hypothesis is true, because that's how we built our sampling distribution on that null hypothesis being true. The fourth and final step is giving our conclusion. Now, this is going to go down two paths. If your p-value is below your level of significance for a problem, typically we use 1 or 5%. So if your p-value is less than your level of significance, then that means we are going to reject the null hypothesis and claim that we do have evidence that the alternative is true. Basically what we're saying is that the sample we found was extremely unlikely. And when something extremely unlikely happens, there's got to be a reason why, and that reason is that the population mean we're assuming to be true is and the alternative hypothesis is correct. Just make sure you say all that in context. Now, the other path is if our p-value is greater than our level of significance. In this case, we're going to fail to reject the null hypothesis. Don't ever say accept the null hypothesis. We still don't know that the null hypothesis is in fact true. We just don't have the evidence to say that it's wrong. Basically, our sample was so close to the population mean that we assumed to be true that we can't officially say that gives us evidence that the population mean is, well, wrong. It doesn't mean we're saying it's right. That's why we say we failed to reject the null hypothesis. We just don't know for sure that it's wrong. And make sure again that you say that in context. And, well, that's it. Those are the 4 steps to doing a significance test for a population mean. Let's look at an example real quick. The makers of a popular caffeine pill want to make sure that their caffeine tablets are being made with the proper amount of caffeine in them. Now, when the machine is operating perfectly, there should be a mean amount of 220 milligrams in every tablet. Now, the manager of the plant is concerned that maybe the tablets are being made with too little caffeine, which would kind of be a big problem. So she decides to get a random sample of 35 tablets, find the sample mean and the sample deviation, and investigate. Does her data provide significant evidence at the 5% level that the machine is working improperly and that the mean amount of caffeine in tablets is less than 220 milligrams? Let's walk through the 4 steps to find out. First, we're going to identify the hypotheses and the name of the test. This is a 1-sample t-test for the population mean amount of caffeine in these tablets produced by this company.